Okay, so moving on to some other very basic concepts like the Boyle's law. So we have learned the Boyle's law before, which states that at any system, if we keep the temperature constant and we keep the number of moles in that system constant for a gas, then the product of the pressure and the volume is a constant. So it's an extremely simple concept. Like if you have a piston system like this, right, and you keep the temperature constant of the system and you keep the number of moles constant, you apply pressure to this piston, the volume will be decreased. It's as simple as that, right? Intuitively, you can understand. Like if you apply more pressure, the volume is going to decrease. So this is mathematically represented as pressure into volume is equal to constant. You might have learned this using a different equation like P1 V1 is equal to P2 V2, right? It's the same thing. P1 V1 is equal to P2 V2, which means like if you know the three, you will be able to exactly determine the fourth one given the temperature and the number of moles is constant. Now this can be represented like this mathematically, in which you have pressure and volume, and PV is equal to constant is like a mathematical function which mimics xy is equal to constant, right? Like if you have x and y constant, which gives us a hyperbola, right? A hyperbola. So a hyperbola has this kind of a shape, right? In which PV is equal to constant. So if you have high pressure, the volume is going to decrease, and if you have high volume, the pressure has to decrease. Like if you have low pressure, the volume increases, and you have high pressure, the volume. So this is a rectangular hyperbola, right? So xy is equal to constant. Similar way, PV is equal to constant. Now, if you have two different states in which temperature 1, temperature 2, so at both different temperatures, this will be valid. PV is equal to constant will be valid, and they will have two different sets of parabolas, right? So PV is equal to constant here, PV is equal to constant is here along this line, along this path. So this is as simple as the Boyle's law. The next one is a Charle's law or Gay-Lussac's law, which operates at pressure and number of moles constant. So this has to be constant. So when this is constant, the volume can be determined using this formula. Now this might look like a little complicated, but I have written this because this is how Charle's law is taught on our channel and here. Okay, so a simpler form of this is V by T constant. So in here it was PV constant, and here it is V by T is equal to constant. Now, we have learned that this is the reason, this is the formula which led to the discovery of the Kelvin scale, right? Why did we need a Kelvin scale when we already had a degree C and a degree Fahrenheit? So this is the reason. This is the law that led to the discovery of a Kelvin scale, which made things really simpler, the absolute temperature scale, okay? For simplicity's sake, we are just recapitulating that V by T is constant if we have the pressure and the number of moles constant. And this is called the Charle's or the Gay-Lussac's law. The third one, very simple one, is the Dalton's law. The Dalton's law says that if you have any system which has gases in it, say you have gas type A, B, C and D, the total pressure exerted, so if you have a pressure gauge in here and you're measuring the total pressure of this whole system, so each of these gases are individually contributing to the total pressure. Now, the total pressure is just the summation of the individual pressures. Now, A is contributing to the total pressure. B, C, D all are contributing. So the total pressure is just the summation which is given by the sigma of all the individual components, right? So if you have the total pressure will be the pressure contribution of A plus the pressure contribution of B plus the pressure contribution of C and the pressure contribution of D. Now, the reverse way, now if you know the total pressure, which is easy to calculate in here, if you have a pressure gauge that will give you the total pressure, how do you know the pressure contributions from the individual gas molecules, like individual types of gas molecules? That will just be the total pressure multiplied by the mole fraction of that particular type of gas. Okay. Now, what's the mole fraction? Mole fraction is just the number of moles of that particular gas divided by the total number of moles, right? So the number of moles total. Now, for example, if you have 1 mole of gas A, 2 moles of gas B, 1 mole of gas C, and 3 moles of gas D. So now we want to find out the pressure contribution of gas A. The pressure contribution will just be the total pressure into the mole fraction. Now the mole fraction of A would be the number of moles of A, which is 1, divided by the sum, which is 1 plus 2 plus 1 plus 3. So this will just be 1 by 8 of the total pressure will be the contribution of A. Similarly, the contribution of B will be 2 by 8. The number of total moles remains constant, just the number of the mole fraction of B increases. Now, an important thing to understand here is this did not depend on the nature of the gas molecules, right? It could have been any gas and the answer would have been the same. It just depended on the number of moles or the number of molecules these individual gases had inside them. Okay, so the pressure of gas B will be twice the pressure of gas A in the system, just because the number of moles of pressure of gas B is double in here. It's an extremely simple concept. It's a Dalton's law. Okay, now if we combine the two laws in here, the Boyle's law and the Charle's law. So the Boyle's law is PV constant, the Charle's law V by T constant. Now if we put this, the PV by T comes out to be a constant, which is known as the universal gas constant, denoted by a letter capital R. Now how did we find this? How did we get to this point in which we found that PV by T becomes a constant? Through experiments, right? So we did some experiments at lower pressure. Now why lower pressure? Because gases tend to behave more ideally at lower pressures. Why? Because at lower pressures the volume becomes larger. When the volume becomes larger, the individual gas molecules grow further and further apart. And the intermolecular force of attraction between these different particles reduce. And this brings us into the realm of more idealistic gas behavior. Also, more ideal gases, like more of the noble gases, behave more ideally generally. Like if you get the noble gases like helium, neon, and argon, or more unreactive gases like nitrogen, things like that, they will tend to behave more ideally. Okay? Now, when we have lower pressures or higher volumes, now we saw that PV is a constant. Okay? So what we did, we took a particular pressure of 1 atm. So you know the pressure can be denoted by units of atm, atmospheric pressure. So at 1 atmospheric pressure, at a particular temperature, which is the 273.15 or 0 degrees Celsius, at this particular pressure and temperature, any gas always has this volume. Any ideal gas always has this volume. So we did experiments and we always found that this was the number. Okay? You know, we did experiments at 1 bar too. Like 1 bar is slightly less than 1 atmospheric pressure. So at 1 bar and at 273 Kelvin, 1 mole of any gas always measures 22.7 bars liter per mole. So in here you see, like bar is the unit of the pressure, liter is the unit of volume, and this is per mole, right? 1 mole is measuring this. So this volume is called the molar volume, right? Extremely important result. Extremely. So you take a nitrogen gas, 1 mole of nitrogen gas at 1 bar, and you fix the temperature to this will be 22.7. You get nitrogen gas, it will be the same. You get any other ideal gas, and it will always come out to be this. Now, not all gases behave ideally, right? But experiments were done on multiple of these gases, and this is a pretty solid number that always came up, like 22.4 at 1 atm and 22.7 at 1 at 1 bar. So this gave us the concept of molar volume, extremely important result. 1 mole of any gas at these temperature and pressure condition will always give you a fixed volume. Hey, isn't that fascinating? I find that fascinating, okay? Whether it's a small gas like a hydrogen or a helium, or whether it's a bigger gas molecule, it always gives the same number. Absolutely stunning. Okay, now we gave this Vm, we noted this molar volume by Vm. Now, what we did, we tried to find out the ratio of this PVM by T, right? So, we know that this PVM is 22.7, okay? So this is 22.7 and at temperature 273.15, okay? So pressure was 1 bar, volume is 22.7, temperature is 273.15. This is for 1 mole, right? And that is why your units are liter for volume, bar for the pressure, Kelvin per Kelvin for the temperature in here in the denominator, and per mole, because this is for 1 mole, right? So we always get this number, 0.083145 liter bar per mole per Kelvin. Now, we also saw that this can be also represented in other units, okay? So these are the two units that we'll be mostly using, either this or 8.314 joule per Kelvin per mole. So this always came out to be a constant. So we said that, okay, so we rearranged this equation as this. So we know that R is a fixed number. So if we know that R is a fixed number, if we arrange this, this gives us a very important tool, a very important tool in our capability to manipulate or to understand how the pressure, volume, and temperature interchanges. Like if we fix the pressure and the volume, since R is always fixed, we can always give you the temperature, right? Isn't this like fascinating? This is the ideal gas law. Now, let's include the number of moles in here, because so if the volume of 1 mole is Vm, the volume of n number of moles will be n times Vm. So this was true for 1 mole of a gas. If we now have a system which is n number of moles, it will just become, so in place of Vm, you write V by n, V divided by n. So the n is in the denominator in here, this n goes to the right side and becomes PV equals nRT, right? And this is the ideal gas law.